Good morning, students. We are going to see about the transport layer on today. So the overview of transport layer, it is in this slides, you are going to understand the basic principles and the services of the transport layer, multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. We will learn about the Internet Transport Layer Protocol, such as UDP, TCP, and TCP congestion controls. So when we're going to talk about transport layer, the transport layer services, multiplexing and demultiplexing that you had seen already, connectionless transfer protocol, that is UDP, principles of reliable data transfer, connection-oriented transport, that is TCP, principles of congestion control, TCP congestion control, evolution of transport layer and functionalities. So this is called as transport services and its protocols. So the transport layers provide logical communication between the applications and its process that is running on different hosts. For example, the transport layer protocols actions in end-to-end systems. The sender breaks the application messages into segments and passes to the network layer. The receiver reassembles the segments into messages and passes to the application layer. Two transport protocols available to the internet applications such as TCP and UP. The transport versus network layer services and its protocols. Network layer, logical communication between hosts. Transport layer, logical communication between process. It relies on enhances networking layer services. The transport layer and its actions. The transport layer, when it is a sender, it is passed an application layer messages. It determines the segment, header, fields, and its values. It creates segments and passes segments to the IP address. So for example, if the transport layer is going to be an receiver, the receiver segments from the IP, it checks the header values, it extracts the application layer messages and demultiplexes messages up to the application via the socket. So two principles of Internet Transfer Protocols, TCP, Transmission Control Protocol, it is very reliable in order delivery. Congestion control, it has flow control and it is connection setup. So it is when you're going to send information through the TCP, it is reliable, and the flow control is very nominal. Since it is a connection setup, the information will be sent easily. So on the next is UDP, User Datagram Protocol. It is not reliable. It is unordered delivery, no frills of extractions of best effort IP. Services not available. It delays guarantee, bandwidth guarantees. Depends upon the bandwidth guarantees only. We can talk about the principles and its protocols. See in this example, if the information is sent from the client, how it tracks. See here, this is the information which is going to be sent from the server, HTTP server, and the message is sent to the application layer. If the information is being sent from the Apache server, see here, HTTP message is being sent and the header is added to the HTTP message, and after it, it is turned to the the information will be taken to the network layer, and again the header will be added here, and again see here, if all the informations are added and all these information will be taken to the application which is present in the client side. So if the information is being sent like this, see here, all this information is P client is sending information. I mean, this client is sending information to the server, and the server will react for the particular client. And if this particular client is asking something, for this query, the application, I mean, the server will react in a different way. So all these informations will be taken as separate requests. Okay, so this is called as multiplexing and demultiplexing. So multiplexing at sender side, it handles data from multiple sockets and transport headers. So all these informations are collected and it will be transported to the transported header and later used for demultiplexing. So demultiplexing is nothing but it receives information sent from the header, and then it will receive the information and it will segment the information and make it in a correct socket. Okay, so how demultiplexing works, see here. Host receives IP datagrams. Each datagram has source IP address and destination IP address. Each datagram carries one transport layer segment. Each segment has source layers, destination port number, etc. So host uses IP address and port numbers to direct segment to the appropriate socket. See here. So this is the source port and this is the destination port. So the information will be carried out like this. So if it is going to be a connectionless demultiplexing, then you have to write the code to create a connection, and then you have to send the information, and then after sending the information you have to reopen the connection. So to create a connection you have to create a datagram socket. So with the help of the object you can send the information. When creating datagram into the UDP socket, you must specify the destination IP address with the help of this asterisk symbol. When receiving the host receives the UDP segment, it sets a destination port address in the segment, directs UDP segment to the socket with the help of that port port address. IP and UDP datagrams with the same destination port address but different source IP address and or source port numbers will be different. So it will be directed to the same socket at the receiving host. See here, this is the connectionless demultiplexing. For example, I am saying this. So if the information is being sent from this application layer, so the application layer is sending information to the application layer which is present in P1, and see here the P1 is reacting for the same information and it is sending the information to P3. In other case, P4 is also requesting information to P1. So P1 is responding for P4 in another layer. Okay. So the information shared with the transport layer. So if it is going to be connection-oriented demultiplexing, TCP socket identifier, it will have a tuple that is 4 bytes, source IP address, source port number, destination IP address, destination port number. So the demultiplexer uses all the 4 values to direct segment to the appropriate socket. The server may support many simultaneous TCP sockets. Each socket is identified by its own port tuple. Each socket associated with a different connecting client. So this is the connection-oriented demultiplexing example. See here, the information is sent from the what? If anything is being sent from the P1, it will be delivered to P4. I mean the process which is present in the server. So the destination and the port numbers are being given here. So it will be easy to reach the destination. 3 segments, all the designated to IP address P, The designations of port 80 are demultiplexed to different circuits. Okay, and this is a summary for multiplexing and demultiplexing. It based on the segments and datagrams, header field values. The UDP, which is demultiplexing using destination port number only. The TCP, it is a connection oriented demultiplexing using port tuple, source and destination IP address and port number. Multiplexing and demultiplexing happens at all layers. Okay, so this is UDP. UDP is nothing but user datagram protocol. It is not having any frills or bare bones. Internet transport protocol. It use the best effort service. UDP segments may be lost since the delivery out of order to app. Since it is a connectionless oriented, no handshaking between UDP sender and the receiver will be performed. Each UDP segment handled independently of others. So why we need a UDP? What is the need for the UDP? So when there is no connection establishment, which can add RTT delay, simple no connection state at sender or receiver, it will have small header size, so no congestion control, but it is not having any congestion control. UDP can blast away as fast as desired. It can function in the phase of congestions. So UDP datagram protocol. UDP uses streaming multimedia apps, loss tolerant and rate sensitive is there, DNS, SNMP and HTTP3. If reliable transfer need over UDP, example HTTP3, add needed reliability at application layer and congestion control at the application layer. See here, so this is the source port, length, destination port, and let's take some. So, and this is the datagram protocol. So transport layer actions. See here, if anything is sent, the UDP senders action, it is passed an application layer message. It determines UDP segment, header fields, values. It creates UDP segment and passes segment to IP. Okay, so UDP receives actions. So it receives the informations here in the UDP place, receives segmented from IP, and then it will be transferred to transport protocol, transport UDP, and it will, here it will perform the check. UDP checks some header values. So after checking all those informations, extracted application layer, it will send all the information extracted to the application layer above. So the demultiplexes message up to the application via socket. So this is the UDP segment header. So it will have the length in bytes and the UDP segment, it includes the header files. So this is the application data. So this is the checksum of UDP. It detects errors if happens when it is being transmitted to the segmented. So transmission first number, if there is any errors. For example, I'm sending 5611, but it is received as 4611. So sender and receiver is having difference of information. So it is known as this errors caused when it is being transmitted. Okay, so how the errors are detected? The errors mainly occurs only due to the flipped bits in the transmission segment. The sender treats the contents of UDP segment. It includes UDP header, fields, and IP address as sequence of 16 bits. It will have checksum, additions of ones, complement sum of segment content, checksum value put in the UDP checksum field. The receiver, on the other end, compute checksums of the receiver segment. Check if computer checksum equals the checksum field value. If equal, then there is no error. If it is not equal, then the error may be detected. If equals, no error detected, but maybe error nonetheless more later. Okay, this is the checksum example. For example, if we are going to have a 16-bit integer and all these things are added and wrap around, so it is having 1 here. When adding numbers, carry out from the most significant bit needs to be added to the result. So it is added to the result and the checksum value is given, and then it is checked. So 0 and 1, 0 and 1, and ones and zeros. So even though the numbers have changed, bit flaps, no change in checksum. So this is the drawback when we are going to use UDP. So if there are two changes, then it will not show the error. So no frill protocol, segments may be lost, delivered out of order, best effort service, send and hope for the best. So UDP has its pulse, no setup or handshaking needed, no RTT incurred, can function when network service is compromised. It helps with the reliability, that is with the help of checksum. So build the additional functionality on top of UDP in the application layer. So what are the principles when we are going to talk about the reliable data transfer? So sending and receiving messages. So sending process, that is reliable service abstraction. See here, the sending process, the application layer is sending the data, the sender side reliable data transfer protocol. So this is unreliable channel. So if it is unreliable, it may either send or receive informations. And it may have errors. So the complexity of reliable data transfer protocol will depend strongly on the characteristics of unreliable channels. If there is loss or corrupt or reordered data, then it will receive only wrong information. Sender and receiver do not know the state of each other. Example was a message received unless communicated via a message. Okay. See here, if it is being not reliable, so you will not have any information sent or received. Okay. So the reliable data transfer protocol interfaces. So this is the sender and receiving mode. So sending the information through the called pass data to the deliver to receive upper layer. So the information is read. So the information is being sent. So see here, call when the packet arrives on the receiver side, and then call by the RDT to deliver data to the upper layer. So this is the bidirectional communication in the unreliable channel. So it has data, but it has informations. So this is taken as packets. Okay. So reliable data transfer, it is getting started here. So it increases incrementally develops sender and receiver sides of reliable data transfer, that is RDT. It considers only unidirectional data transfer, but control information will flow in both the directions. It uses finite state mechanism to specify sender and receiver state. So it's a selective repeat. So a receiver individually acknowledges all correctly received packets. If it is not correctly received, it will not send any information. So buffers packets as needed for eventually in order to deliver to upper layer. Sender times out or retransmit individually for an unacknowledged packets. Sender maintains timer for each unacknowledged packet. Sender window n consecutive sequences. It limits the addresses of the sent and unpacked messages. So selective repeat and sender and receiver windows. See here. So if it is going to be the window size, so RCV base and the window size. So send base and the next sequences base. So this shows the already acknowledged. This shows sent not yet acknowledged. This shows that it is unstable, not sent, and this shows that it is not usable. So receiver view of the sequence of number. So it is the view of the receiver side. So selective repeat sender and repeater. The sender send the data from the above. If the next available sequence address in the window and send packet, it has timed out, resend packet, restart timer, and it has to acknowledge. And the receiver side, the packet N sends and acknowledges it is out of order in order to deliver the information. Packets in N RCV base N, RCV base 1, acknowledge N, it otherwise ignores. So the sender and receiver side, see here. So the sender is sending the information and the receiver is receiving the information the other end as packets. So this is the acknowledgement of the information sent and received. If they are not, see here, the acknowledgement 3 is not received. So on the next set, the packet time 2 is out. So see here, it sends only one acknowledgement. So selective repeat dilemma. So see here that it is accepting and it is reacting. So it has no problem, but it will accept the packet and send the sequence number. So if the receiver cannot see the sender side, the receiver behave identical in both the cases, then it is right. If it is not identical, then it is wrong. So this is the TCP overview. TCP is used to view point-to-point, end-to-end deliver of information. One sender and one receiver will be there. It is reliable in order byte stream. So no message boundaries for it. It was full duplex data. It is bidirectional so that it can send and receive informations in both the side at the same time. And it has maximum segment size. So it has cumulative acknowledgements. It has pipelining. It is connection oriented. It is flow controlled. So the segments of the TCP, see here, this is the source port and this is the destination port, and it will have sequence number to find out the packets, and this is acknowledgement to the sender and the receiver. The application data sent by the application and TCP cycle. Okay, see here the TCP options are here. The length of the TCP is there. The RST, RYN, and FIN connection management. So it receives the windows. Okay, so this is TCP segment structure. So TCP sequence number. So sent, acknowledged, sent, not acknowledged, usable, not usable. All these things are discussed here. Okay. So TCP sequence number for host A and host B with a simple telnet scenario. See here, sent and receive the informations. So TCP round trip time turned on. How to set TCP timeout longer than RTT, but RTT varies too short premature timeout. Unnecessary retransmission of data will occur. Too long, slow reaction to segment loss. So sample RTT measured time from segment transmission until acknowledgement receipt. Okay, this is TCP round trip time, not timeout. This is the formula to calculate the round trip time. See here, this is the round trip to send and receive data. Okay, so here This is nothing but safety margin. This is estimated RTT. So total time interval. So see here, this is the formula to apply. So sender and TCP sender. So event data received from application, it creates segment with this sequence. Sequence is a byte stream number of first data byte in its start timer if not already running. So event timeout, event acknowledged. So event timeout is used to restart the timer. Acknowledgement is used to acknowledge the information received. So event at receiver and TCP receiver. So delayed acknowledgement, it has to wait up to 500 milliseconds for next segment. If no next segment, send acknowledgement. Okay, the arrival of in order segment with the expected sequential, none other segment has acknowledgement pending. Arrival of out of order segment higher than the expected sequential order, its gap is being detected. Immediately send duplicate acknowledgement in TCP receiver. Its indication sequence hash of next expected byte. So this is the retransmission scenarios of TCP and its acknowledgement, the timeout being calculated. So this is the retransmission of data. This is used for the fast transmission of information. If sender receives 3 additional acknowledgements for the same data, triple duplicate acknowledges send and acknowledged segment with the smallest sequential address. Likewise, the system will be lost. So TCP protocol, application layer, TCP socket, after receiving the buffers, TCP code, IP code. Okay. So the information is sent through the application layer, and it will has to travel to the layers below. So this TCP flow control. TCP receiver advertises free buffer space in rewind field in TCP. TCP buffer size set via socket optionals. So it sends a limited amount of unacknowledged data to received rewind. It guarantees the received buffer will not overflow. Okay, so the TCP connection management. Before exchanging data, sender or receiver has to handshake, agree to the established connection. It agrees on connection parameters. The socket line socket is equal to new socket, host name, port name. So this is application layer, connection state, ESTAB, connection variables, sequential client to server, server to client, RCV, buffer size at server client. So this is just to explain you the two-way handshake signals. Okay. So let's talk. So if they are going to talk, he will react for information, and it will be established that they both talk. If the other end is not responding, then it will not be correct. So the two-way handshake scenarios. So this is the two-way handshake scenarios, and the information sent to these CPU, and it reacts for the estimation amount which is sent by the user, and it will send the accepted data of the range. And the next is establishment of information through the request and acknowledgement. So tree transmission will also be occurred at this stage. Okay, so this is the other method. See here. So problem with the data. So this is the client and server side programming. So this is the HTTP three-way handshake programming. See here, when they are climbing, they are all disturbing. So client server each close their side of connection. It sends TCP segment with the FIN bit is equal to 1. Respond received FIN acknowledgement. And receiving FIN acknowledgement can be combined with own FIN. Simultaneously, FIN exchanges handle data. And the next is the principle of congestion controls. Informally, too many sources sending too much of data too fast for a network to handle. It is manifestation. It has long delay. It has packet losses, different flow of control, a top of 10 problems. It causes cost congestion in scenario 1. See here. So if anything is sent from host A to host, anything information received from the original data and it is being sent to the throughput. See here. It causes cost or congestion scenario. One router finite buffers. The sender retransmits last timed out packet. Application layer input is equal to application layer output. That is lambda n is equal to lambda out. Okay, this is original data. This is plus retransmission. So original data plus retransmission will be taken into account. So this is the throughput. So this is the data transfer method. See here how it is being transformed. So the causes and cost of congestions. So throughput can never exceed the capacity. Delay increases at the capacity approach. Loss or retransmission decreases effective. The unneed duplicates further decreases the effective throughput. This is the upstream transmission capacity buffer wasted for packets last streaming. So these are the approaches towards congestion control. So it has end-to-end congestion controls. So no explicit feedback from the network. Congestions infer from the observed loss delays. So the the data is being transmitted to the other layer. So and after the data is being received, the acknowledgement is sent to the same layer. So the approach taken by TCP/IP to avoid and the data transmission delays. So the network assassinated congestion controls. The routers provide direct feedback to send a receive host with flows passing through the congested router may indicate a congestion level or explicitly send sending rate. So see this the information being passed. So explicit congestion information is being sent through on the TCP, ECN, ATM, DE deficit, etc. So the TCP congestion control AIMD approach senders can increase sending rate until packet loss congestion occurs, then decrease sending rate on loss events. So the sending and receiving information. So the additive increases. So the increases be shown here. The multiple decreases, it is also being shown here. AIMD, the truth. the behavior, the behavior is probing for bandwidth. So the multiplicative decrease detail sending rate is cut in half on loss detected by triple duplicate ACK, cut one by MSS when loss detected by timeout. So YAIMD, a distributed asynchronous algorithm, has been shown here. So this is the congestion control details. Last byte acknowledged, sent by not yet acknowledged, last byte sent, available but not used. So these are the informations being given by the TCP. The TCP sender limits transmission bytes. So CWND is dynamically adjusted in response to the observed networking conditions. So this is the TCP slow start. Main condition begins. Initially, count as one MSS, double count RTT, done by incrementing CWND for every acknowledgement received. So this is the acknowledgement received and it is being summarized here. So TCP flow start to the congestion avoidance. So the TCPs, the implementation is variable SS thresh and loss even SS thresh is set to half count and before a loss event. See here, this is the SS thresh. So this is the summary of TCP congestion controls. It's slow start and it will be sent to and receive the information. So fast recovery of data can be done with the help of TCP congestion. This is TCP cubic that we had already seen about AIMD. So the same occurs here. Is that a better way than AIMD to probe for unusable bandwidth? So WMAX sending the rate with the conjunction loss was detected. And after the cutting edge, the window in half on loss initially ramped to WMAX faster than the approach. It was slowly more. Okay, see here. So TCP cubic, K point in time, when TCP window size will reach WMAX, K itself is tunable. Increase W as a function of cube of the distance between the current time and K. Large increases when further away from K, smaller increases when nearer K. Okay. So this is TCP and congested bottleneck link. So TCP classical and cubic, TCP sending wait until packet loss occurs at some router's output, the bottleneck link. So this is the packet queue, almost never empty, sometimes overflows the data. So bottleneck occurs due to the congestions. Understanding congestion useful to focus on the congested bottleneck. So TCP insight increase the sending rate will not increase and end improve throughout the congested bottleneck. So delay based TCP congestion control, keeping sender to receive pipe just full enough but no fuller. Keep bottleneck link busy transmitting, avoid high delays. Delay based approaches, RTT, minimum observed RTT, uncongested throughput with congestion controls. So delay based TCP congestion control without including forcing or losing, maximum throughput keeping the just pipe full while keeping delayed low but not fuller. So TCP fairness goal, if K TCP sessions share some bottleneck link, bandwidth R, each should have average rate. This is TCP pair. Two contempting TCP sessions, additive increase gives slope 1 as throughput increases. So multiplicative decreases the throughput proportionally. So this is the proportional event which is occurring. So fairness must all networks apps be fair. So fairness that multimedia apps often do not use TCP. It is connection oriented. Applications can open multiple parallel connections between TCP host. So there is no So there is no intent policies use of congestions. So web browsers do these things. Example, link of the rate R with 9 existing connections. New apps, 1 TCP gets R by 10. New apps as 11 TCPs gets R by 2. So this is that's all about transport layer. We will meet in the next class. Thank you.